So hello everybody, welcome to our session of the Necas Continuum Mechanics Seminar, and today's speaker is Petr Pelech from the Weierstraße Institute in Berlin, and he's going to speak about Penrose-Fife model with activities phase change, existence and effective model for slow loading.
Okay, so I hope everyone can hear me. If not, then please tell me immediately. First of all, thank you, Martin, for an invitation, and good afternoon to everybody. It's my great pleasure to give a talk here at Necas seminar at Charles University, my alma mater. I will be speaking today about my joint work with Matthias Diego and Alexander Mielke from Weierstraße Institute. And in the first part, I would like to introduce you to the Penrose-Fife model, what it describes, and why we consider it. And in the second part, I will focus on the so-called balanced viscosity solutions, which are exactly a notion of solution for a rate-independent process appearing as a limit of vanishing viscosity. So, classical Penrose-Fife model was the first consistent model which coupled Allen-Kane equation for a phase field with thermal effects in a thermodynamically consistent way. So I was surprised that until 90s this problem hadn't been solved. It may describe a mean field model of Ising ferromagnet or some metallic order-disorder transition. The unknowns are the internal energy and the phase field, and in the system, kappa stands for thermal conductivity, and temperature here introduces the coupling for a very special choice of entropy, the logarithmic entropy. This is more or less the temperature. I have to say I'm skipping here all the physical constants. Yeah, so whenever you need some physical unit, feel free to introduce it. We have it just one here everywhere. And the phi stands for potential, which describes the phase transition of Z. So this is the boundary value problem we are solving. So we have a normal heat equation with thermal diffusion, Allen-Kane equation for the phase field, Laplacian for the interfacial energy, the derivative of the potential as the driving force, and 1 over theta here couples the system to the temperature we have. And we have closed system, which means we have no flux boundary condition on the whole boundary. This model has been thoroughly investigated already. The global existence was first proved in 1993 by Spreckels and Zeng. And then, since then, many other papers appeared, and some authors to mention are Lorenzo, Krejci, Weierreiser, Schiperna, Rocca, and so on. For our setting, it's important that the system poses a gradient structure. What this means will be clear, I hope, at the end of this slide. The first structure was formally introduced by Alexander Mielke a few years ago. And the viscosity space was properly set up after 5 years. It took some time. That means that the rates of internal energy and the phase field lies in the dual of H1 times L2. So we have the viscous space for the phase field is L2, but this H1 dual is, for me, it was a surprise to work with such a space. So, and this viscosity space for rates, we denote XPF for Penrose-Fife space. We consider the total energy, which is simply the total value in this chart, E and Z, and a total entropy. That's one of the entropy considered by Penrose and Fife. So this is the thermal and entropy for stemming from thermal effects, and this is the entropy due to the phase transition and phase transformation. For the system, this of course increases in time, but we prefer rather to work with the so-called exergy. Some people call it free energy, and the reason for this is that this functional is coercive in the functional space. So for this we use the variation methods. The last thing we need to define is the dual dissipation potential, which is defined on driving forces, which are in duality to the rates. So that's the dual space to the viscous space, and the key point here is that it's not state dependent. It doesn't depend on E and Z. It just takes here the differential with respect to E and differential with respect to Z, differential of entropy, and it's quadratic. So the first term is responsible for heat production. This then yields the conservation law of the conservation of energy, and the Allen-Kahn equation has just a L2 scalar product. And we denoted the by duality and some operator K. Yeah? So that's a quadratic functional. And why is it a gradient structure? Because the rates are given by the differential of the driving functional, exergy in our case, and then the differential has to be mapped from the dual space to the cotangent space to the tangent space. So this is in quadratic case nothing but where we have Hilbert space structure. This is the Rees isomorphism. So in using the K notation, that's the equation, and for regular solutions, this is nothing but the classical formulation. Just a short digression about the energy or exergy functional. That's the form which appeared. Well, entropy appeared on the slide before, so that's the exergy, the energy minus entropy, and it's defined here. It's considered E as L1 function. However, this function, it's not Laplace semi-continuous with respect to the viscous topology. This was the H1 star times L2. So what we can use that if the phase field potential is semi-convex, which means if you have the double well, this point, there is no kink. Yeah, it's not approximated by minus the absolute value. It's smooth. Yeah, the second derivative is bounded from below by some constant. Then this function is semi-convex, and by some abstract theorem, one knows that there is also a semi-convex Laplace semi-continuous extension, which is fine, but there is something to work with. But it brings some more difficulties because in 3 dimensions, we have. I mean, the point is that F has just linear growth in the energy, which is stemming from the energy part here. That's the minus entropy. And here's the total energy. And hence, the domain of this Laplace semi-continuous envelope contains measures. Yeah, we have sequence bounded in L1, which means there is, subsequent convergence weakly in measures, and not all of them are contained. Those spaces are just not subordinate in any sense. Yes, only nice measures are considered. Yeah, for example, measures concentrated on nice surfaces. Because for a nice surface, well, you have trace theorems. So we have a trace, and hence on this measure concentrated on this surface defines a nice function on H1. But point measures like Dirac measures supported on a point or line are simply not contained in H1 star. If one is interested, the full characterization of those nice measures was given in the book by Zimmer, Properties of Weakly Differentiable Functions. But luckily, just for existence theory of this classical Penrose-Fife model, classical because it doesn't contain this this activation, the activation of the phase transformation. So we don't need it. We don't need the full characterization. It's enough to have some abstract functional, and then the existence follows. There is exactly one global solution, and it depends continuously on initial data. Just a short comment, because we were also interested, and we needed for other works how the functional looks like actually. So that's the form we use. And if you take E in the H1 star and Z in L2, so that's how the function is defined. We decompose E, because it's also a measure, using the Lebesgue decomposition. So F stands for the absolutely continuous part, and E perpendicular for the singular part. And here in the old formula, we plug only the absolutely continuous part, and here comes the singular part. Yeah, this is just the total mass. This comes from the total energy. So this E perpendicular, this F comes together, but also the functional is plus infinity otherwise, which means in particular that the singular part is not in positive, non-negative measures. Yeah, so because the logarithm is plus infinity at minus infinity, yeah, it has a singularity. Minus infinity is completely excluded, but f minus this logarithm has linear growth at plus infinity. So only concentrations, so the measures can concentrate only at plus infinity. So only positive non-negative measures are allowed here. The formula is long. The point is that it's the old formula with here the total measure. Here's only the absolutely continuous part, and here responsible for the plus infinity is the indicator function, which takes the singular part, and K stands for the cone of non-negative measures in H1 star. So it seems good, this formula, yeah, but the question is whether F and E perpendicular are good coordinates in our setting, which means whether the projection, which assigns to a measure its singular part, is continuous in H1 star, because that's our viscous space, that's our topology. And the answer is unfortunately not. No. So one just cannot simply differentiate this functional as one wishes. We just know that along the solution, of course, at almost every time, there's, there is the subdifferential is not non-empty, the freshly subdifferential, and there is some subderivative lying in it, but that's all we know a priori. The problem is that in general, the unit ball of H1 of functionals in H1 star is not bounded in measures. Yes. And the only positive thing we know that in a special case, which luckily we are in, if the absolutely continuous parts are bounded from below and the singular parts are non-negative, then we have boundedness. Yeah? Then the projection is a bounded map. But the projection is not linear, it's not defined on a linear space, so non-continuity follows. And the simple counterexample here is that everyone knows, yeah, so that L1 functions can concentrate in the big topology in measures to a Dirac measure. Yeah, so but this converges weakly star in measures. However, this sequence, precisely the very same sequence, converges strongly in H1 star. And hence one cannot expect even strong weak continuity of the projection. Yeah. Even supposing strong convergence doesn't deal anything about the images. So this was everything about the classical model. The new thing in the classical model in our case would be just, the closure of the definition domain, that we consider the measures which may appear. So we have we closed it, and now I would like to say something about the activation of the phase transformation. So according to Bergquist's paper, if there are impurities or immobile dislocations in the material, the movement of the phase front is harder, and there is some threshold which has to be overcome. Yeah? Below this threshold, if you force the phase to transform, and the driving force is not strong enough, then nothing happens. So this is done by the standard tri-friction term. So if you consider this rate independent dissipation functional defined on the rate of Z, which is more or less the absolute value, then the subdifferential is the sine function here. It's a Z-valued friction force, because if it doesn't move, then you may apply some force which is simply not high enough. But if it moves, then you have to apply precisely the high force. Yeah, so it cannot be lower, otherwise it would be at rest, but it also cannot be higher. Yeah, this subdifferential is not surjective. But that's just this is just a part of our system. We also have the viscous quadratic term. So this is how the supplemented system looks like. Here's the new term appearing. So this driving force has to be high enough to overcome the dry friction. And this is how the dual dissipation potential is then changed. So it's still, in the first coordinate, it's still quadratic, but here for the driving force of the phase field, we have this H rho function. The formula is difficult, but it means that until the threshold, this threshold rho is reached, it's zero, it's constant zero, and then it grows quadratically. So this is the nonlinear behavior, which is included, and this was the system we investigate. So far we've proved existence of solutions. We did it with the energy dissipation principle and incremental minimization scheme. So the energy dissipation principle just reformulates the equation from this gradient flow, which is an equation in Banach space. We reformulate it equivalently as a scalar equation. You know, this equality is actually an optimality condition, but the point is that it's not a complicated object in a Banach space. It's just a scalar equation. That's why it's easier to treat. And the solution of the problem satisfies this relation. Yeah, so the exergy at the beginning equals the exergy at the final time plus the dissipated energy along the way. Yeah, there's one technical issue that we have, how the energy, how the dissipation potentials are defined. But the main point is that if we have energy conservation, then our primary dissipation potential is equivalent to the norm in our viscous space. Yeah, and hence it works good together, all the topologies. The difficult part here was that we could not use the standard theory due to Colley and Sintin, because the state space, which is somehow connected to the coercivity of the exergy, is not compactly embedded in the viscosity space of the rates. Yeah, because the measures here are the troublemakers. Yeah, if it were L2 star, then it holds, but we doesn't have it. Yeah, we don't have quadratic growth, it's just linear. But the good point here is that the equation for E is linear. Yeah, so this we could use, and then using I would say a minty trick kind of argument, the existent follows. Now, so of course it was important that it was quadratic and also decoupled properly. So this is the first result we have, and now I would like to turn to the ongoing work, and that's the vanishing viscosity analysis. So imagine that your system is no longer autonomous, but you apply some force on the phase field, but you do it very softly, slowly. You give enough time to the system to accommodate, and so you push it a bit, then the system relaxes to equilibrium again, then you push it a bit, and then it changes again. So then if we rewrite it, yeah, in mathematics, this means that we have some small epsilon here in the system. So the quadratic dissipation potential then is rate dependent. So it also, if the process is slow, then the terms are also slow, but the rate independent term doesn't scale, so it doesn't depend on epsilon. And the problem is that as epsilon goes to 0, the system becomes somehow degenerate. Why we want to investigate such a system? Simply because for most of the time, loading is small and the viscosity can be neglected. It doesn't play a role. However, if the limit system develops a jump, then the viscosity becomes very important. So that's effective model we want to derive, where the viscosity is not seen, only at some important parts. So this is our scale dissipation potential we have, and using the standard bounds, we see that independent of epsilon, we have bounded energy. Yeah, for almost every time. We have coercivity of the exergy, so the energy space, which is measures for energy, and H1 for the phase field, is valid. We have also some from dissipation, this rate independent dissipation estimate. So z dot is bounded in L1, L1. However, if we look for bounds for rate of energy, we have just from the viscous dissipation this L2 viscous space bound, which however blows up with epsilon, which means there may be jumps, which is no problem for the Z component, yeah, because this is known that this is just the standard rate independent theory. This bound is enough to use some selection principle and to have enough compactness. So here Z stands for a candidate. This can describe the effective behavior of the system, but this we have only for the Z component. What's the effective behavior of the internal energy? We have no temporal compactness so far. And the second point is, of course, one has to, although the internal energy is almost at equilibrium at every time, this holds only where there is no jump. But along the jump, you have to resolve the whole jump. Then the viscosity activates again, and the energy and the phase field may even interact. And so the interaction is has to be somehow included in the effective model. So the idea how to even describe the effective solution is to use the arc length parameterization. Yeah, so instead of function of time, we define the length of the curve. So this is not, if you move this t under the integral, then it's 1 plus this norm. So it is really nothing but the norm of the tangent vector, and in the product space, yeah, of time, which is 1, and the rates. And in the Banach space for rates, we use this viscous number, of course. But because it's a norm of the vector, we have just power 1 here. And that's the difference to this bound, to this viscosity bound, where we have power 2, and this cannot be bounded. But with power here 1, there is a hope. So that's how it looks. We have epsilon solutions of the viscous problem, but as viscosity vanishes, the solution may develop jumps. So until at some point there is some abrupt change. But if we do just this, you just cannot say what's happening along here. We don't have enough information. However, if we do this reparameterization, which, I mean, a good point is that it's also by construction Lipschitz, then we have in the limit that the solution evolves, and the time also along the curve increases, but at some point the time stops, and that's of course the jump, and we can see how along the jump the solution interact with each other. Yeah, and of course, if one wants, we can go back to reuse the system and just investigate the phase field and the internal energy. So that's the arc length parameterization switch for a function of time. to a curve. So then this whole curve going from here and there and here is the solution, and it's parameterized by S. Just to have some definition, what we mean by balanced viscosity solution. So we have to have some viscosity space, some energy functional on the viscosity space, some viscosity operator, and some rate independent dissipation potential. Then we say that the curve of time and the state is a parameterized PV solution if the time is parameterized appropriately, which means it's non-decreasing, it's zero at zero, and it reaches the final time at the final arc length. And moreover, there exists actually Lagrange multiplier lambda, which somehow triggers the behavior. So if lambda is zero, then you have normal rate independent system. But if lambda is non-zero, the viscosity again appears, is activated, and of course it has to really switch between rate independent and rate dependent behavior. So this has to be zero. So either lambda is zero and then time can increases, or time stops and then there is a jump and then lambda may be non-zero. However, both of them can be also zero, which means we have a jump, but a jump where the viscosity is not important, it doesn't appear. And given this extended solution, we can do by projection introduce the so-called enhanced PV solution. We just throw some information away if we want. How this works? So if one introduces this parameterization, then we just rewrite the energy dissipation balance using the arc length. So we have, lots of terms here, but the important thing is that here we have, as epsilon as the upper limit of integration, and here in front of the viscosity, we have epsilon over the time derivative here. So this is what somehow activates in the limit the viscous dissipation, and also the friction force here is scaled, and one also has to be scaled the loading. And this is what we want to know, what the limit of this scalar equation is. And the main problem is to show that in the limit, S epsilon doesn't blow up. So the length of the curve in the topology we chose remains bounded. So for simplicity, we consider some, just to explain it, a bit simpler system, but we have for the state given by energy and the phase field, we have the energy space given by the coercivity of the exergy, and viscous space given by the dissipation potential by the dissipation, and the same for Z. In our case, we have the viscous space is H1 star times L2, and the energy space, for simplicity, as I said, is not composed of measures intersected in H1 star, but let us think for a moment that it's L2. It's a good thing. Then the theory is known, and this is something we would like to make it that it really behaves like this system, and this we do by restricting the temperature. That we will prove that the temperature remains bounded in L infinity. So there's some theta star. If you have, of course, nice initial conditions. and then the linear growth at infinity is not seen. It doesn't make problem. Yeah, and improving the bound of the arc length. So the first good news is that the the activation of the phase transformation we introduced by this rate-independent dissipation potential is actually not visible at all, because if we differentiated the equation we have for z in time and then test it by z dot. So this is of course given by the second derivative, and yeah, I mean this is in quotation marks. So we interchange the second derivative, so z dot and z double dot is switched, but this term is zero. So I hope to explain this behavior on this simple setting. A term z dot is zero, and then this term is zero and no one cares. But if it's non-zero, then as one moves along the rate, the friction force is constant, which means its derivative along z dot is zero. So this term is then zero. So this is why the rate independent term in this estimate, in these estimates, doesn't play a role. It disappears. Second thing is we have energy which is convex in E. Yeah, that's and semi-convex in Z, because we need stronger assumptions on the convexity in E, because we do not have the temporal control. There was no bound on E dot, and hence we control the behavior of energy by its convexity. Yeah, because if you tilt it, then the state cannot change so much. Yeah, tilting convex potential doesn't move the solution so much if it's I mean highly convex. But if it's almost flat, then the solution changes a lot. But with convexity, it's good, and for Z, because we have this rate independent bound, just semi-convexity is enough. So this is what we need, at least in the viscous space, to have some bound. And this is due to semi-convexity. We can afford in the Beaker norm, in the L2 norm, some defect. And the third ingredient is so-called interpolation of rates, and this is how we treat this defect. We can estimate it by something we can absorb in this energy estimate, and by something we have bounded a priori. That's the rate independent dissipation potential. So this how everything puts together, and we obtain in the end bounds on the arc length, which was, I mean, the viscous norm, the length of the tangent vector in viscous norm, but with power 1, not 2. And this brings me to the end of my presentation. So we investigated small viscosity Penrose-Fife model with dry friction term, and we were investigated in its effective behavior. Yes, viscosity vanishes. Its limit, yeah, we want to describe by so-called balanced viscosity solutions, which are somewhere in between fully rate independent system, which one can recognize here, and there is still a reminder of the original viscosity system. Yeah, the viscosity can be switched on, but only if the time stops and one finds on jump. The difficulty we have is that we do not have uniformly convex potential in energy. Yeah? So it's linear at infinity, and hence we have to deal with measures and have to work more in the a priori estimates on the arc length. So far, we finished the existence theory for positive viscosity, and now we're working on the passage as epsilon tends to 0. So this is still work in progress. And yeah, I mean, an interesting question, of course, is if one has uniqueness of solutions of the viscous system. So epsilon is positive, but we don't have the classical Penrose-Fife model, which, as I've shown you, has this Lipschitz dependent on continuous data. We have this rate independent term on top of it, and then we don't know whether viscosity with this rate independent friction still yields uniqueness. So that's still open question for us. Now I would like to thank you for your attention, and if there are some questions or comments, I'm very happy to hear them or answer them.
So thank you very much, Petr, for your interesting talk, which is now open for questions and remarks and comments. So if there is a question or comment, so please feel free to ask, or just I don't see anybody in the chat.
So may I
Yeah,
ask a question?
Tomáš.
So,
yeah, so go on.
At the beginning, you somehow wrote that free energies difference, maybe slide 4. Or, yeah, exactly. Yeah, it's a difference of energy and entropy.
Mm-hmm.
You know, it's very exotic for me because if nothing else, so energy is in joule and entropy is joule per Kelvin. So
Sure. I should have also said it again. Just for simplicity, I skipped all the units. So of course, in front of the entropy, there has to be 1 over temperature. That's because of energy.
no, it should be temperature, not
Just temperature. Okay, temperature, and it's a fixed temperature in this case. Yeah, and just for our purpose, for having coercivity, we don't mind. The temperature can be.
But you do not have fixed temperature. Eh? In the bottom, you have 1 over temperature. Temperature is a variable, is it?
And that's the difference between free energy and our exergy. If it were free energy, then you're completely right. There has to be temperature in front of the entropy as a variable.
No.
But because we define exergy, which is a different functional, we have
Okay, but also entropy is different. You shouldn't call it entropy, because otherwise you cannot sum it up. It has different physical meaning, different units. No?
And if I had some theta star here in front of it, then it would be fine.
No, okay, no, sure, no, simply, no, you shouldn't call it total entropy. It's something different. And by the way, entropy shouldn't contain stored energy.
No, sorry, total entropy is really entropy. That's the line above. Yes, it's the logarithm term minus the phase field.
It has different units, and simply also the meaning. So stored energy normally does not contribute to entropy.
Okay, so you're asking in this line with total entropy why there is this phi and this gradient.
No, for example. No.
Yeah. I mean that's the original entropy introduced by Penrose and Fife, and if you do it so, I believe it's correct. I mean, Penrose wrote it so, but if you do it so, then you really left alone only the thermal effects. Yeah, if if
Okay, but
he writes it originally in free energy, with real free energy, with in temperature, and the point in writing it so is that then you have a total energy. Let's say you put aside the energy which is hidden in the phase field, and the energy you are left in, this is the energy which is responsible for thermal effects. This is how I remember it works. So